Hi everyone, today I will discuss about electrolytic conductance. So let us see what do we mean by electrolytic conductance. Now before I discuss electrolytic conductance, let us see what actually electrolytes are. So what are electrolytes? So electrolytes are the substances that dissociate in aqueous solution. So substances which dissociate in aqueous solutions. Aqueous. Now, these electrolytes can be strong and weak. So, if I talk about strong electrolytes, so strong electrolytes are the one that have alpha, that is degree of dissociation, nearly equals to 1. That means they are almost completely ionized. So, I'm writing almost completely ionized, right? Alpha is nearly equals to 1 or 100% dissociated or ionized. In the case of weak electrolytes, alpha, is very less than 1. Yes. So it ionizes only to a little extent. Yes, ionizes to a little extent. For example, in the case of strong electrolytes, we have like for say NaOH, HCl, right? We have NaCl. We also have salts like CaCl2 because this salt or these type of salts for say magnesium chloride, these salts do not precipitate in the solution. So we consider it in the class of strong electrolytes. Then we have weak electrolytes for say NH4OH, CS3COOH, salts like barium sulfate, because you know that these salts precipitate out in solution, and AgCl, etc. And we also know what are non-electrolytes. Non-electrolytes are the substances which do not dissociate in aqueous solution, for example, urea, sugar, etc. So, when I talk about electrolytic conductance, basically if I see conductance, so with conductance I mean the flow of electric current, and this flow of electric current can be because of the flow of or the movement of ions and the movement of electrons. So if I talk about the metallic conductance, there the flow of electric current is because of the flow of electrons, whereas in the case of electrolytic conductance, it is ions that are flowing and results in the flowing of electric current. So with electrolytic conductance, the flow of electric current is basically due to the flow of ions. Due to the flow of ions. Yes. So it is due to the flow of ions. Now, and how do we represent it? It is represented by G. It is represented by G. So if I say what is G, G is basically electrolytic conductance. It is the ease of flow of current due to the movement of ions. Due to the movement of ions. And there is one term which is resistance. So conductance, electrolytic conductance is the ease of flow of electric current, whereas this resistance is the hindrance or obstruction in this flow of current. So it is the hindrance to the flow of current. Yes, to the flow of current. Now, so can I say that G is equal to 1 by R? Yes, G is the inverse of R. Now we also know We also know that R is equal to rho L by A. Yes, we also know R is equal to rho L by A, where rho is the resistivity of a substance, resistivity or specific resistance of a substance. This is a property of a substance. Yes, of a substance. Yes. For example, this is my electrolytic cell, right? And these are my electrodes, anode and cathode. This is the electrolytic solution. So let us say the distance between this is your L, and the area of cross section is equal to A, is represented by A. So A is the area of cross section and L is the distance between the two electrodes, right? So R is equal to rho L by A. Also, we know that for R, the unit is ohm, or you can also write it ohm. The unit is ohm. So can I say that for electrolytic conductance, the unit becomes per ohm, or you can also write it per ohm, MHO, or Siemens. So Moho or Siemens, right? So Siemens is the unit of electrolytic conductance. Yes, Siemens is the unit of electrolytic conductance. Now, just like resistance is equal to rho L by A, we have basically now. So there is electrolytic conductance, and then comes your electrolytic conductivity, or what we call specific conductance. Specific conductance. This specific conductance is your kappa, and this is basically your conductivity. This is your conductivity, and it is equal to 1 upon rho. It is equal to 1 upon rho. So suppose if I consider this to be equation number 1, so reciprocal, we just find the reciprocal of this. So this is 1 by R is equal to 1 by rho into A by L, right? Now 1 by R is your G, that is your conductance. 1 by rho is kappa, that is your conductivity, and this is A by L. Now if you take this, if you take A by L to the LHS, so this becomes G into L by A is equal to kappa. Now this L by A is your cell constant. This is your cell constant, right? This is a cell constant, and it is represented by G star. It is represented by G star. So can I say G into G star is basically your kappa. G into G star is your kappa. So what is conductivity? That is equal to electrolytic conductance multiplied by the cell constant. Now if I talk about the unit of kappa, then what is this? The unit of G is Siemens, and cell constant is basically centimeter inverse. If I measure the length and area in terms of centimeter, right? So this is Siemens per centimeter or Siemens per meter. So this is the unit of kappa, right? This is the unit of kappa. Now G. Now we have this expression G is equal to kappa into A by L. Now what I am doing is I am multiplying and dividing the RHS by L. So what it is? So multiplying and dividing RHS by L. And what do I get? G is equal to kappa A by L and L by L, right? So this is, so you know that area into length is nothing but volume of the electrolytic solution, right? So this becomes G is equal to kappa into volume upon This is L square. If you take it to the right hand side, this becomes G into L square is equal to kappa into volume. Now, if length is equal to, if L is equal to 1 centimeter, if L is equal to 1 centimeter, then it becomes G is equal to kappa into volume. Kappa into volume. This is the volume of the electrolytic solution. So if I define kappa, that is conductivity, what is that? Basically, conductivity or specific conductance is the conductance of 1 centimeter cube of a electrolytic solution, because if volume is 1, if volume is equal to 1 centimeter cube, then G is nothing but kappa. So this kappa is electrolytic conductance of 1 centimeter cube of the electrolytic solution. Now we define a term which is your molar conductance. Now we define a term which is molar conductance, that is lambda m. Now what do we mean by molar conductance? It is basically the conductance of 1 mole, conductance due to 1 mole of ions. It is the conductance due to 1 mole of ions, right? 1 mole of ions. So what I am doing is, suppose, so if I divide this equation, so let us say this is equation number 2. So if I divide 2 by n, that is number of moles, what do we get? This is G upon n is equal to kappa into V by n. Now G by n is basically your lambda m. This G by n is nothing but your lambda m, because this is the conductance due to 1 mole of ions, right? And what is this? This is kappa. So because this becomes your molar conductance. Similarly, V upon n becomes your molar volume, right? This becomes your molar volume. Yes or no? This becomes the molar volume. Now we also know that if you, like for example, if you have concentration, for say molarity. So molarity is number of moles per unit volume. Yes, number of moles divided by volume. So can I write that this is G by n, or lambda m is equal to kappa into V by this is Vm, right? Now can I write this concentration as 1 upon, can I write this as 1 upon V upon n? Yes, can I write it like this? Yes, we can. So this is a molar volume, and molar volume is nothing but kappa into V by n, right? Kappa into V by n. And if you take V by n this side, so V by n is nothing but 1 upon C. So basically lambda m becomes kappa into 1 by C, or kappa upon, this is important, kappa upon C, right? Now look here. If I say what is the unit of this lambda m, molar conductance? So we know the unit of kappa, that is Siemens per centimeter, right? Divided by concentration. For say molarity, here in this case molarity is defined as mole per liter. Mole per liter. And we also know that at room temperature 1 liter is nothing but 1000 cc, right? It is equal to 1000 centimeter cube. 1000 centimeter cube. So if I want to find out the unit, I will write it like this, mole, right? And in place of liter, I will write 1000 centimeter cube, right? So what do I have? This is Siemens centimeter per centimeter divided by mole into centimeter. It is minus centimeter minus 3, and that 1000 will go up, right? That 1000 will go up. So this becomes Siemens centimeter square per mole. It is basically Siemens centimeter square per mole. This is the unit that we have got for lambda, right? Or we can also find out this unit from here. That lambda m is equal to kappa into molar volume. So this is simple. So we can also find the unit from here. This is Siemens per centimeter and this is centimeter cube per mole, because this is molar volume, right? Centimeter cube per mole. So this becomes Siemens centimeter square per mole. So we can also find it like this, right? But please remember that you don't remember this basically this factor of 1000. Don't remember this factor of 1000. Just remember this formula. Why? Because because suppose if the cell constant is of the unit meter -1 or meter inverse, then in that case that 1 liter is 10 to the power -3 meter cube, right? 10 to the power -3 meter cube. So please do not remember this 1000 factor. Just remember the formula that lambda m is equal to kappa upon c, and you can convert the units in the question itself, right? Just write the values for kappa, just write the values for this concentration, molarity, and you can convert it accordingly. So please remember this particular formula. Do not remember this factor of 1000, right? This factor of 1000 is this is applicable when the cell constant is having the unit of centimeter inverse, or kappa is having the unit of Siemens per cent. Sorry. Now, similarly, just like polar conductance, we have electrolytic conductance, which is equal to kappa upon normality. Kappa upon normality. And if I ask you what is the unit of this equivalent conductance, then this is Siemens centimeter square, and instead of per mole, you have per gram equivalent. Per gram. So this becomes the unit for electrolytic, this equivalent conductance. Right? So I hope this topic is clear to you. Yes. So what is electrolytic conductance? Electrolytic conductance is the flow of current due to the movement of. Okay. So thank you so very much. To take care.